The first misunderstanding begins with the photograph. When people see a deep image from Hubble or James Webb, the universe can look crowded beyond reason. Every patch seems filled with galaxies. Every dark gap seems to hide more light, and the frame gives the impression that matter must be spread densely across the whole cosmos. But the image is showing something very specific. It is showing the places where matter emits, reflects, or bends light strongly enough for our instruments to detect. Hubble's deep field looked at an extremely small patch of sky, about 1/13 the diameter of the full moon, and still revealed thousands of galaxies because the telescope stared for a long time into a region that only seemed empty at first glance. That did not prove the universe is packed everywhere. It proved that if you look deeply enough at a small patch, you can uncover distant luminous structure that ordinary vision would miss. This distinction matters because a telescope image is not a census of typical space. It is a record of successful detection. Deep field images are designed to find faint galaxies, not to teach human intuition what average cosmic volume is like. The bright knots dominate our attention because that is what cameras are built to collect. The long stretches between them do not advertise themselves with the same force. When NASA describes the cosmic web, it does not describe a universe filled smoothly and uniformly with matter. It describes galaxies, groups, clusters, superclusters, and galactic walls arranged in twisting, thread-like structures, with voids of space in between. James Webb results describing the earliest strands of the cosmic web use nearly the same picture. Galaxies gather in vast filamentary structures with gigantic barren voids between them. The scale of that emptiness begins close to home. Even our own solar system is mostly distance. Neptune orbits far from the Sun by ordinary human standards, yet the planetary region is still only a local inner district of the Sun's much larger sphere of influence. NASA's Oort cloud facts say the Oort cloud occupies distances from about 5,000 to 100,000 astronomical units from the Sun, and NASA's scale infographic explains that beyond the outer edge of the Oort cloud, the gravity of other stars begins to dominate the Sun's. In other words, if you include the broad icy shell of the Oort cloud, the solar system reaches far beyond the planets people usually picture. And even then, the nearest Sun-like stellar system, Alpha Centauri A and B, is still about 4.3 light-years away. That comparison is more important than it first appears. If the outer edge of the Oort cloud may extend to around 100,000 astronomical units, that is roughly 1.6 light-years. Alpha Centauri lies about 4.3 light-years away. So, even after allowing the Sun its enormous distant cloud of icy bodies, there is still a vast interval before the nearest comparable star system begins. This is not a small crack between neighboring objects. It is a dominant feature of the local universe. The luminous bodies get remembered. The intervals do most of the spacing. The same pattern grows harsher when we move from stars to galaxies. A galaxy photograph can look busy because each point is not a star in your local neighborhood, but an entire galaxy, often containing billions of stars. That alone can distort instinct. A frame crowded with galaxies is not showing a packed, solid cosmos. It is showing rare, luminous concentrations distributed across immense depth. NASA's Large-Scale Structures page says the cosmic web forms as gravitational attraction draws matter together into larger and larger objects, producing concentrations of galaxies with voids of space in between, almost as if the galaxies were resting on empty bubbles. NASA's sheets and voids explanation goes even further and says surveys reveal a bubbly structure in which filaments of galaxies form a twisting web punctuated by large voids that may fill about 95% of space. This is why the phrase observable universe can mislead if it is heard too casually. It sounds like a full sphere whose contents should be crowded simply because we can observe them. But observability is about whether light has had time and ability to reach us, not whether matter is densely spread everywhere within that volume. NASA's Hubble Deep Field Material and XDF material both emphasize that extremely deep observations reveal faint, distant galaxies by integrating light for very long periods. That is a triumph of sensitivity. It does not imply that the volume between those sources is filled the way water fills a tank. There is another visual trap hidden in the flatness of images. Astronomical photographs collapse huge depth into a two-dimensional frame. Objects that appear side by side may in fact be separated by millions or billions of light years along the line of sight. The eye reads the frame as surface crowding, but the universe is three-dimensional and staggeringly deep. In that geometry, many bright points only seem adjacent because they are projected onto the same patch of sky. Deep images therefore train the eye to see abundance, which is real, but they do not automatically train the mind to feel separation, which is even more important for this topic. The cosmic web description from NASA only makes full sense when that depth is restored in thought. Bright nodes, linked filaments, and large voids together define the real map. It also helps to notice how astronomy chooses its targets. Telescopes are rarely pointed at average, nothing for no reason at all. They are used to answer questions, and those questions often lead astronomers toward regions where something measurable is happening: star formation, galaxy assembly, lensing, explosions, ionized gas, black hole activity, or faint sources at great distances. Even when a field is chosen because it looks dark and empty at first, as with the original Hubble Deep Field, the experiment is really asking whether deeper exposure will uncover hidden structure. That means the public image archive of the universe is naturally biased toward places where matter announces itself. The unannounced reaches remain physically dominant but visually underrepresented. Once this correction begins to take hold, the phrase, "the universe is mostly empty," stops sounding like an exaggeration. It becomes a statement about average density and large-scale arrangement. Matter exists. In fact, there are astonishing numbers of stars and galaxies, but they are not spread like grains in a tightly packed block. They are organized into separated systems, larger networks, and immense low-density regions. NASA's descriptions of the cosmic web say exactly that: concentrations where matter gathered, voids where it did not remain dense, and a structure shaped by gravity across cosmic time. A universe can contain enormous numbers of galaxies and still be mostly empty, in the sense that most of its volume is not occupied by dense, luminous matter. This is why the contrast between the solar system, Alpha Centauri, and the cosmic web belongs at the start of the story. The planets already show that even a familiar stellar system is built on spacing. The gap to the next star system shows that stars are not packed together the way people casually imagine. The cosmic web then shows that galaxies follow the same broad rule on much grander scales. Structure exists, but it exists as islands, filaments, knots, and walls separated by huge underdense volumes. The universe looks full in pictures, because pictures favor the bright addresses. The deeper physical truth is that brightness is local, while separation is widespread. So the first shock in this subject is not that astronomy exaggerated. It is that human perception overtrusted what a dramatic image seemed to imply. The galaxies in those images are real. The clusters are real. The glowing gas is real. But the impression of crowding comes from looking at the rare places where matter has become visible to us across impossible distance. Most of the universe is not like the center of a deep field image. Most of it is the long interval between such places. That is why the cosmos can look crowded on a screen and still turn out to be almost empty when the problem is stated in terms of volume, spacing, and average density. With that revised picture of the early universe in mind, another problem becomes difficult to ignore. The young universe was once far hotter and denser than it is today. Under such conditions, matter might appear likely to remain distributed more evenly. Yet what we observe instead is a universe where galaxies form scattered structures separated by vast stretches of space. That contrast brings us to, if the Big Bang made everything, why didn't matter fill the universe evenly? At first, the Big Bang seems to promise a very different universe from the one we see. If everything began in an early state that was far hotter, far denser, and far more compressed than anything we can picture from ordinary life, then instinct suggests that matter should have ended up spread everywhere in a fairly even way. It feels natural to imagine an early cosmic fireball expanding outward, like steam in a room, thinning with time but remaining broadly smooth. Yet the actual universe does not look like that. Galaxies are gathered into clusters. Clusters are linked by filaments, and between those structures lie immense regions where matter is much harder to find. The first thing to understand is that the Big Bang did not create a finished map of galaxies. It created conditions, ingredients, and tiny initial differences, and over the next 13.8 billion years, those differences were amplified until matter collected into structure instead of remaining evenly spread. NASA describes the universe as about 13.8 billion years old, and both NASA and ESA explain that the oldest observable light already preserves slight early variations that later became the seeds of galaxies and larger structure. This is where the picture becomes more precise and more interesting. The early universe was not chaotic in the everyday sense. It was remarkably uniform on large scales, but not perfectly uniform. That difference matters. Perfect uniformity would have left gravity with almost nothing to work on. If matter had been distributed in exactly the same density everywhere, then every region would have pulled on its surroundings in a nearly balanced way, and large structure would have struggled to emerge. But the early universe carried tiny irregularities. They were extremely small, yet they were real, and later they became decisive. ESA's Planck mission describes the cosmic microwave background as a snapshot of the universe when it was about 380,000 years old, showing tiny temperature differences that correspond to slightly different densities. Those denser and less dense patches were not random decoration. They were the starting pattern from which stars, galaxies, and galaxy clusters eventually formed. The scale of those early irregularities is one of the most important details in all of cosmology. They were incredibly small. NASA's COBE results describe the fluctuations in the cosmic microwave background as only about 1 part in 100,000 relative to the average temperature of that radiation field. That means the young universe was astonishingly smooth, but not featureless. A 1 part in 100,000 contrast may sound too tiny to matter. In daily life, it would be tiny. In cosmology, given enough time and the persistent action of gravity, it was enough to change everything. Regions that began just a little denser had slightly stronger gravitational pull. That allowed them to attract a little more matter. Once they became denser, their pull increased further, which let them gather still more matter. This is the quiet logic behind structure formation. Tiny differences did not stay tiny. Gravity kept reinforcing them. To understand why expansion did not erase those differences, it helps to hold two processes in mind at the same time. The universe was expanding, and gravity was competing with that expansion locally. Expansion caused average density to fall. Matter was spread through a growing volume, so the cosmos as a whole became thinner with time. NASA explains that the early universe passed through a period of very rapid inflation and later continued expanding over cosmic history. But expansion did not scrub away every unevenness after it was established. Instead, it stretched space while gravity worked inside that expanding framework, gradually drawing matter into the slightly overdense regions. So the universe did become thinner overall, but not smoother in the long run. On large scales, the mean density dropped. On smaller and intermediate scales, structure grew. These two facts are not opposites. They are parts of the same history. That history also explains why the universe changed so dramatically between its first few 100,000 years and the later ages filled with stars and galaxies. When the cosmic microwave background was released, the universe had cooled enough for light to decouple from matter. Before that moment, the universe was dense, hot, and opaque. NASA states that the cosmic microwave background originated about 380,000 years after the Big Bang, when the universe was still dense, hot, and opaque, and that we observe that same light today stretched by expansion into a glow of about 2.7 Kelvin. James Webb materials from NASA add another important detail. At the time COBE and WMAP were observing that heat signature, there were still no stars and galaxies yet. In other words, the early pattern was in place before luminous structure had formed. The universe first had to cool, then let matter gather, then slowly build the first stars and galaxies from those initial density contrasts. This is one reason the cosmic microwave background matters so deeply. It is not simply old light. It is a measured record of how smooth the early universe was, and exactly how imperfect that smoothness turned out to be. Missions such as COBE, WMAP, and Planck did not merely confirm that the early universe was hot. They mapped the fine pattern of unevenness across the whole sky. NASA says WMAP produced the first fine-resolution full-sky map of the microwave sky and determined the age of the universe to within about 0.5%, while Planck refined the picture further. Those maps let cosmologists test how much ordinary matter exists, how much dark matter contributes, how close the geometry of space is to flat, and what sort of primordial fluctuations best match the later universe. The fact that galaxies exist at all, and that they are arranged in a web, rather than as an even mist, is tied directly to those faint patterns. There is also a subtle point here that often disappears in simplified retellings. The Big Bang did not explode matter outward from a center into pre-existing empty room. Rather, space itself expanded. NASA's overview of cosmic history describes the universe expanding from an early, hot, dense state, with inflation as an early phase that helps explain large-scale properties we see now. That distinction matters because it changes the way evenness should be imagined. Matter was not flying through a fixed void like debris from a firework. The whole cosmic stage was evolving. Within that changing stage, tiny primordial density variations were stretched to large scales and later became the pattern that gravity worked on. ESA states that these fluctuations were stretched to cosmological scales during inflation and later served as the seeds of the structure we now observe. So why did matter not remain smoothly diluted everywhere? Because smooth dilution is only part of the story. Expansion lowers average density, but gravity rewards even slight excess. A region that starts a tiny bit ahead in density becomes a slightly better collector of surrounding matter. Over time, that advantage compounds. Matter streams toward denser zones, and as it does, neighboring regions are left more depleted. This is how the universe develops contrast. It is not that emptiness was inserted as a separate ingredient. Emptier regions appear partly because matter is being drained toward denser ones. ESA describes the slightly denser regions in the early universe as becoming increasingly denser because gravity caused them to draw more and more matter from their surroundings. That single sentence contains much of the logic behind why today's universe contains both rich structures and broad empty reaches. A useful way to feel the scale of the transformation is to compare the early universe with a landscape before weather has done its work. Imagine a surface that looks almost level, except for tiny rises and shallow depressions too small to impress the eye. Then imagine water flowing across it for an immense span of time. The water does not create every feature from nothing. It takes the faint pattern already present and exaggerates it. Low areas become channels. High areas lose material. Over long periods, a surface that once looked nearly flat develops valleys, ridges, and drainage networks. Cosmology follows a related logic, though the actual physics is gravity acting on density within expanding space, not water flowing over ground. The point is that a very mild initial pattern can evolve into a dramatic later structure if one process keeps amplifying the original contrast. This also helps explain why the phrase, "the Big Bang made everything," is true but incomplete. It made the early universe, not the finished arrangement we see around us. The stars overhead, the galaxies in survey maps, the clusters measured by observatories, and the long filaments reconstructed from millions of redshifts are the result of cosmic history unfolding step by step. The Big Bang set the initial state. Inflation likely stretched primordial fluctuations to large scales. The universe cooled. Light decoupled at about 380,000 years. Matter continued responding to gravity. Dark matter, which does not shine, provided additional gravitational scaffolding. Gas later fell into halos, stars formed, galaxies assembled, and the large-scale web emerged over billions of years. None of that requires the early universe to have been wildly uneven. It only requires it not to have been perfectly even. The early universe was smoother than almost anyone expects, yet not smooth enough to prevent structure. The later universe is emptier than pictures suggest, yet not empty enough to prevent gravity from weaving matter into a vast connected network. Those two facts fit together. The smooth beginning explains why the cosmic microwave background looks so uniform. The slight departures from that smoothness explain why the modern universe contains galaxies instead of remaining a featureless fog. NASA and ESA both present those faint early fluctuations as the seeds of all future structure. And once that point settles in, the present-day mixture of dense regions and sparse ones no longer feels like a contradiction. It feels like the long outcome of tiny differences given billions of years to grow. When that picture is taken seriously, another point becomes clear. If gravity gathered matter into stars, galaxies, and clusters, then it must also have influenced the regions where matter became scarce. The dense parts of the universe were growing, while the emptier regions were taking shape at the same time within the same expanding cosmos. That realization leads us to, did gravity create the empty parts of the universe as much as the full ones? When people first hear that gravity built the large structures of the universe, they usually imagine only the crowded side of the story. They picture gas falling together, stars igniting, galaxies assembling, and clusters growing heavier as more matter is pulled inward. That part is true, but it is only half of what gravity has been doing for billions of years. The same pull that builds the dense places also helps empty out the thin places. Gravity does not simply create fullness, it sharpens contrast. It gathers matter into knots, threads, and walls. And by doing that, it leaves neighboring regions more depleted than they were before. That is one reason the universe came to look like a cosmic web instead of a smooth fog. NASA describes the large-scale universe as an interconnected structure of filaments and sheets, with galaxies gathering in larger structures rather than being randomly scattered, while ESA describes the cosmic web as dense filaments and clusters interspersed with gigantic voids. This becomes easier to see once you stop thinking of gravity as a force that acts only at the destination. It also changes the surroundings on the way there. Imagine matter in the early universe spread almost evenly, but not perfectly evenly. Some regions begin slightly denser than average. Others begin slightly less dense. As time passes, the denser regions attract more material. That incoming matter has to come from somewhere. It flows out of nearby space. So while one region becomes richer, another becomes poorer. The same process is doing both jobs at once. NASA's description of the cosmic web says it started out tenuous and became more distinct over time as gravity drew matter together, leaving gigantic barren voids in between. ESA makes the same point from another angle. Matter is arranged in huge clusters linked by dense filaments and separated by enormous underdense regions. That is why the empty parts of the universe are not an afterthought. They are part of the architecture. A cosmic void is not just a patch where nothing interesting happened. It is a region that became increasingly underdense, while surrounding structure grew more pronounced. In other words, the voids were shaped by the same history that shaped the clusters. This is not just theoretical language. The Sloan Digital Sky Survey reported observational and simulation-based work showing that voids became emptier because gravity pulled matter away from them toward denser boundaries. That result matters because it tells us the depleted regions are not merely places where telescopes fail. They are genuine outcomes of structure formation. Seen from far enough away, the universe begins to resemble a kind of tension pattern. Matter is not laid down like paint on a flat surface. It is drawn into pathways. Filaments stretch across enormous distances. Where several filaments meet, clusters of galaxies build up at the intersections. NASA says filaments and sheets of matter create the large-scale structure of the universe, and ESA describes galaxy clusters as the densest knots of that web. Once that picture settles in, a striking fact appears. The web is not made only of the bright strands. It is made equally by the spaces between them. Without the low-density regions, the web would not look like a web at all. This is also why astronomical images can be so misleading at first glance. A telescope naturally highlights where matter emits light, bends light, or heats surrounding gas. It shows the dense nodes, the luminous galaxies, the crowded cluster cores. But the large-scale map of the universe is defined just as much by what is missing from the neighboring volume. A road map is not only the roads, it is also the land between them. In cosmology, the filaments are striking because the surrounding regions have been drained. NASA's Hubble work on mapping the cosmic web emphasizes that large-scale structure is web-like, not uniform, and earlier, Hubble results produced three-dimensional maps showing dark matter distributed in a web pattern rather than spread smoothly. Dark matter plays an important role here as well. Ordinary gas and stars are only part of the story. Much of the gravitational scaffolding is invisible to ordinary telescopes, but its effects can still be traced. NASA's Hubble dark matter mapping described dark matter as accounting for most of the universe's mass and showed that it follows a web-like large-scale distribution. That means when gravity is pulling matter into filaments and clusters, much of the pull is associated with structures that do not shine on their own. Ordinary matter tends to fall into the gravitational pattern already outlined by dark matter. Gas collects, cools, forms stars, and lights up the places where the deeper structure had already begun to gather mass. So when we say gravity built the full regions and emptied the thin regions, we are talking about a process involving both visible matter and a larger invisible framework. The emptier regions are therefore not simple absences. They are records of flow. Matter has been moving away from them in the long statistical sense, feeding denser structures elsewhere. Over billions of years, that changes the geometry of the universe on large scales. Small early fluctuations grow into a network with strong contrast between rich intersections and depleted interiors. NASA's Roman mission description says Roman will help reveal how the universe transformed from a primordial sea of charged particles into the intricate network of vast cosmic structures we see today. That phrase is important because it reminds us that the web was not always sharp. It had to emerge. The voids, too, had to deepen. There is a useful shift in perspective here. Instead of thinking that gravity made galaxies and then left empty regions behind as leftovers, it is more accurate to say gravity sculpted a full pattern of highs and lows. Dense regions rose in contrast, while underdense regions fell away in contrast. Both trends belong to the same mechanism. ESA's description of the cosmic web says matter forms a wispy network of clusters and dense filaments interspersed with gigantic voids. The word interspersed matters. It does not describe two unrelated populations. It describes one connected pattern. Modern surveys are making that pattern easier to test with far greater detail. NASA announced in December 2025 that the Nancy Grace Roman Space Telescope will observe thousands of newfound cosmic voids, with measurements precise enough to help constrain cosmological models. Roman is valuable here because voids are sensitive probes of how matter grows and how cosmic expansion competes with gravitational collapse. If the dense parts tell us where matter won, the thin parts tell us how far that process went and under what cosmic conditions. NASA's statement makes clear that voids are not fringe objects in cosmology. They are part of the evidence used to understand the universe as a whole. The scale of this becomes hard to hold in mind, which is one reason the cosmic web feels abstract until it is described carefully. A galaxy cluster is already enormous. A filament linking clusters can stretch across distances that make a single galaxy look small by comparison. A void can span tens of millions of light-years or more, and yet none of this required gravity to work in two different ways. One process is enough. Matter drifts towards slightly denser regions. Those regions become better at attracting more matter, and the neighboring space becomes more rarefied. Over long times, the contrast strengthens. Fullness and emptiness rise together. This is one of the reasons the phrase large-scale structure is more revealing than it first sounds. Structure means pattern, but pattern always involves both presence and spacing. A necklace is not only the beads, it is also the intervals that let the beads form a sequence. The cosmic web is not only the galaxies and clusters, it is also the underdense stretches that separate and define them. NASA's Webb findings on very early strands of the cosmic web suggest that even in the young universe, galaxies were not scattering at random, but were already gathering into larger connected arrangements with barren voids between them. So the contrast between dense and depleted regions was not a late decorative feature. It began developing early and became more distinct over time. There is also something important here for the broader theme of emptiness. Space is not mostly empty because matter failed to form structure. Space is mostly empty, in part, because structure formed so effectively. Once gravity begins to gather matter into favored lanes and intersections, the surrounding volume is left with less. In that sense, the empty parts of the universe are not evidence against gravity's success. They are one of its signatures. The denser the web becomes, the more clearly the voids stand out beside it. ESA's descriptions of clusters as knots in the web and voids as gigantic depleted regions make that balance clear. So the next time an astronomical image makes the universe look crowded, it helps to remember what the image is not showing directly. It is not showing the average condition of cosmic volume. It is showing the places where gravity concentrated matter enough to leave bright evidence. The wider map includes the opposite result as well. The regions gravity steadily emptied by feeding those brighter structures. That is why the cosmic web is one of the clearest answers to the problem of apparent fullness. Gravity did not merely create the crowded parts. It helped create the emptier parts too, and the universe we see today carries both results in the same connected design. Once astronomers began examining those enormous voids more closely, another issue came into view. Some of these regions extend across millions of light-years, yet they still belong to the same cosmic structure that contains galaxies and clusters. In that setting, the word empty starts to lose its ordinary meaning. How can a cosmic void be millions of light-years wide and still not be truly empty? The word void makes the mind do something too quickly. It hears absence and turns that into nothing. It imagines a region scraped clean of substance, light, structure, and physical meaning. But that is not what astronomers mean. A cosmic void is not a hole punched out of reality. It is a vast region where matter is far less concentrated than average. The distinction sounds small at first, yet it changes everything. NASA explained in December 2025 that the Nancy Grace Roman Space Telescope should be able to detect and measure tens of thousands of cosmic voids, including some as small as about 20 million light-years across. ESA also describes cosmic voids as gigantic regions between the strands of the cosmic web, with sizes reaching hundreds of millions of light-years. These are not tiny defects in a crowded universe. They are part of the main structure of the universe itself. To feel the scale properly, it helps to slow the number down. A void 20 million light-years wide is not merely large in the everyday astronomical sense. It is so large that light, moving at about 300,000 kilometers per second, would still need 20 million years to cross it. In the framing NASA used for Roman, that same span is about 120 trillion miles, or about 190 trillion kilometers, a region that large sounds like it should deserve the word nothing. Yet even there, the physical universe has not disappeared. What has disappeared is dense clustering. What remains is thinner, harder to see, and often easier to overlook. This is where a cosmic void becomes more interesting than its name suggests. Even where galaxies are sparse, space-time is still there. Gravity still operates. Radiation still passes through. The cosmic microwave background still fills that region, just as it fills all directions of the observable universe. NASA materials on the cosmic microwave background state that this faint afterglow permeates the universe in all directions, and John Mather's NASA explanation says the CMB fills the universe and travels in all directions. So even in a void that seems visually barren, the oldest light we can observe is still present. Empty to the eye does not mean empty to physics. There is also matter in a void, only much less of it. Astronomers have known for a long time that the space between galaxies contains intergalactic gas. NASA's Cosmic Origins spectrograph materials describe long filaments traced by galaxies and intergalactic gas, separated by huge voids that are not totally empty, but instead contain far less concentrated matter. Another NASA summary explains that quasar light passing through the intergalactic medium can reveal the structure and composition of otherwise faint material between galaxies. That means when a region is called a void, astronomers are not claiming it contains no atoms. They are saying the density is low enough that galaxies are rare and the remaining material is thin, diffuse, and difficult to detect directly. That thin material has shown up in observations in more than one way. One older NASA-linked study of Lyman alpha absorption reported an absorber located inside a void, more than 5.9 megaparsecs from the nearest bright galaxy. That matters because it shows that even where bright galaxies are absent, intervening gas can still leave a measurable signature in the light from a more distant source. The void was not featureless. It was simply faint. This is one of the recurring patterns in cosmology. The universe often looks emptiest where our eyes are least equipped to register what remains. Dark matter makes the story even less intuitive. A void has less matter than average, but that does not mean it has no dark matter at all. NASA's Dark Matter Overview says dark matter makes up most of the matter in the universe, and ESA's Euclid Overview describes the cosmic web as consisting of clusters connected by strands of gas and invisible dark matter, with cosmic voids between them. In standard cosmology, voids are underdense in both ordinary matter and dark matter, but not stripped completely clean. They still sit inside the same gravitational universe as everything else. Gravity does not stop at the boundary of a sparse region. It still shapes motions through and around that region, even when the amount of matter is far below average. This is one reason Roman's void survey is so valuable. Voids are not only empty-looking zones to be catalogued for completeness. They are precision tools for testing how structure grows and how cosmic expansion unfolds. NASA's Roman team says these void measurements can help scientists distinguish among competing explanations for cosmic acceleration and improve tests of dark energy models. A dense cluster tells us where gravity gathered matter effectively. A void tells us what happened to the surrounding volume while that gathering took place. The filaments and the voids are a matched record, two sides of one long gravitational history. The phrase "not truly empty" also applies at a deeper level than gas and dark matter. Modern physics does not treat vacuum as a simple philosophical blank. NASA's Dark Energy Overview states plainly that space is never exactly empty. In that explanation, quantum field theory allows transient particle-antiparticle activity associated with vacuum energy. Whether or not that vacuum energy fully explains cosmic acceleration is still unsettled, but NASA's wording is important here. Even where there are no stars, no nebulae, and no visible galaxy crowding, space itself is not a mere nothing. It carries fields, geometry, and physical properties. So a cosmic void is not outside physics. It is one of the places where physics becomes harder to see because fewer bright objects are available to announce it. There is another trap hidden in the language of emptiness. We tend to treat a void as though it should be sharply bounded, like an empty room with walls. Real cosmic voids are not like that. They are statistical regions, defined by being significantly underdense compared with the average cosmic matter distribution. Their edges are often gradual, marked by rising galaxy counts and growing density as one approaches surrounding filaments and walls. In that sense, a void is less like a hole in fabric and more like a basin in a landscape of density. NASA and ESA descriptions of the cosmic web support this picture. Matter is arranged into strands and concentrations, with large depleted volumes between them, rather than into neatly carved compartments. Once that picture is in place, the emotional force of the subject changes. A void no longer feels like an embarrassing gap in the universe. It becomes a major clue to how the universe organized itself. In the early cosmos, matter was distributed much more smoothly. Over billions of years, gravity drew matter toward denser regions. As a result, filaments thickened, clusters grew, and neighboring regions were left increasingly depleted. That is why a void can become enormous without becoming truly nothing. It is the large-scale outcome of matter relocation, not the erasure of the underlying universe. NASA's Roman work and ESA's cosmic web descriptions both support this view of voids as natural components of structure formation, not exotic exceptions. There is something else worth noticing. Human attention is drawn to what shines, collides, or explodes. That bias makes clusters and galaxies feel like the main story. But voids dominate far more volume. ESA notes that these empty spaces make up more than half the volume of the universe. That means if you chose a random large-scale location in the universe, you would be far more likely to land in a sparse region than inside a dense, luminous one. In that sense, the visual universe shown in popular imagery is the minority environment. The emptier regions are not just background, they are the more common setting. And still, even there, the universe refuses to become nothing. The cosmic microwave background passes through. Weak gravity remains. Thin gas can still reveal itself through absorption. Dark matter is still expected to contribute some share of the mass distribution. Space-time still defines distances, motion, and geometry. Vacuum still carries physical significance. A void may contain few galaxies, but it does not sit outside the cosmos. It is part of the cosmos at low density. That is a more accurate and more useful idea than the older instinct that emptiness means absence in every sense. So when astronomers speak about the biggest empty regions in space, they are not describing pure nothingness stretched across impossible distances. They are describing a thinner kind of reality. A reality where the bright landmarks are scarce, where matter is far less concentrated, where detection becomes difficult, and where the structure of the cosmic web is defined as much by what has been drained away as by what has gathered. The word void survives because it is useful shorthand, but the actual physical picture is richer than that word suggests. A cosmic void can be millions of light years wide and still contain the basic ingredients of the universe. It is empty only by comparison, never by absolute meaning. If a void can still contain gas, radiation, gravity, space-time, and likely dark matter, then the universe may be much less empty than human eyes have been trained to believe. Is the universe empty, or is most of it just invisible to human eyes? By this point, the word empty has already begun to lose its old certainty. First, it became clear that the bright parts of the universe are only scattered islands inside a much larger dark expanse. Then it became clear that even a cosmic void is not stripped clean of physical reality. But here, the correction grows sharper. Much of what we call empty may not be empty in the useful scientific sense at all. It may simply be non-luminous. NASA's current overview says ordinary matter makes up only about 5% of the universe, dark matter about 27%, and the rest is thought to be dark energy. In another NASA glossary entry updated in February 2026, baryonic matter, the ordinary atomic matter that makes up people, planets, stars, and gas, is listed at 4.9% of the universe's mass energy, while dark matter is listed at 26.8%. That single set of numbers changes the emotional center of the story. The stars, planets, nebulae, galaxies, dust clouds, oceans, mountains, cells, and hands that seem so substantial to us are built from the smallest slice of the cosmic budget. The overwhelming majority is not the familiar kind of matter that shines, absorbs light in ordinary ways, or forms the visible surfaces that human beings evolved to notice. So when the universe appears empty to human eyes, the appearance is shaped by a serious observational bias. Eyes are tuned to visible light. Telescopes, even when expanded into infrared, radio, X-ray, and other wavelengths, still rely on measurable signals. But dark matter is called dark precisely because it does not reveal itself by shining. NASA says dark matter makes up most of the mass in galaxies and galaxy clusters and is thought to shape the cosmos on large scales, organizing galaxies and cosmic objects. This is where Vera Rubin's legacy belongs with full force. Her work helped turn the hidden side of the universe from suspicion into a central fact of cosmology. The Smithsonian recently described her as the astronomer who revealed the universe's hidden mass, noting that she made her name by studying what could not be seen directly. That description is exact in the deepest way. Rubin and her collaborators studied how stars move in galaxies and found that the visible matter was not enough to explain the observed rotation. The outer parts of galaxies were moving too fast for the luminous mass alone. Something else had to be there, providing extra gravity. That is why her well-known line lands so naturally in this part of the story. Science progresses best when observations force us to alter our preconceptions. The preconception in this case was very human. We assumed that what shines is what matters most. It is an understandable mistake. Light is how astronomy began. It is how the sky first became legible. but the deeper measurements kept pressing in another direction. NASA's Hubble dark matter page says dark matter is thought to be the scaffolding that normal matter arranges itself around and upon, a web woven through the universe whose gravity attracts normal matter. Another NASA page explains that scientists think dark matter exists in a vast web-like structure winding through the whole universe, a gravitational scaffold that attracts most of the cosmos' normal matter. That means the visible universe may be more like frost collecting on an invisible framework than like a complete inventory of what exists. Once that picture settles in, the word empty begins to fracture into two very different meanings. One meaning is visual. A region looks empty because it does not shine strongly. The other meaning is physical. A region contains very little matter or energy of any kind. Modern cosmology repeatedly warns us not to confuse the two. A region that looks dark may still sit inside a dark matter halo. A gap between visible structures may still be crossed by ancient radiation. A galaxy cluster may owe much of its gravitational behavior to mass that cannot be photographed directly. NASA's Hubble material says gravitational lensing and related techniques have helped map dark matter throughout the cosmos, including three-dimensional maps showing its clumpy, web-like distribution. The eye would never infer that structure from visible light alone. Dark matter is only one half of the invisible side. The other half is stranger still, because it does not merely add hidden mass. It changes the expansion history of the universe itself. NASA's Dark Energy Overview says the expansion of the universe began speeding up roughly 9 billion years after the Big Bang, and that dark energy is the name given to the unknown cause of this acceleration. NASA's Hubble Dark Energy page states the same thing in plainer language. The universe is not slowing down under gravity on large scales, but speeding up faster and faster, propelled by something still not understood. So even if you removed all the ordinary matter you can see, and even if you accounted for dark matter's gravitational scaffold, you would still not have completed the modern cosmic inventory. The large-scale behavior of space itself points toward another dominant component. That is why the phrase invisible universe is not a dramatic exaggeration. It is a fair first approximation of the evidence. The visible part is real, but it is the minority share. NASA's composition graphic from Hubble states that dark energy is the main ingredient of the universe. Dark matter is the next largest constituent, and the rest consists of ordinary matter. Most of that ordinary matter is locked up in stars and clouds of gas, while only a tiny fraction of it makes the heavier elements that planets and human bodies depend on. This means that the surfaces closest to our experience are built from one of the smallest cosmic fractions. They feel central only because they are where we happen to live. There is a useful discipline in stating this carefully. Dark matter has not been bottled in a laboratory and labeled with a known particle identity. Dark energy has not been reduced to a settled microscopic theory, but the absence of full explanation does not erase the strength of the observational case that something beyond ordinary visible matter is required. NASA's Roman dark matter page says the universe must contain more than 5 times as much dark matter as normal matter to fit the observations, and NASA lists multiple lines of evidence for dark matter: the motions of stars and gas, the behavior of galaxy clusters, and gravitational lensing. For dark energy, NASA points to the observed accelerated expansion of space. So the invisible universe is not a poetic guess. It is the name we give to the large share of reality that shows itself indirectly through gravity, expansion, and other measurable effects, rather than through familiar, visible emission. This is also where the older habit of trusting brightness too much starts to look almost provincial. Human eyes evolved on the surface of one planet around one star. They are excellent for daylight, motion, contrast, faces, and nearby objects. They are not built to measure mass energy inventories of the cosmos, so the universe did not become mostly invisible because reality is hiding from us. It became mostly invisible because the methods needed to uncover it go beyond direct seeing. Weak lensing reveals distorted paths of light. Rotation curves reveal unexpected speeds. Cluster dynamics reveal excess gravity. NASA's Hubble and Roman materials repeatedly return to this point. The hidden matter is inferred from what it does. It bends, pulls, shapes, and organizes even when it does not glow. That brings us back to the title of this part. Is the universe empty, or is most of it just invisible to human eyes? The strongest answer is that much of what first appears empty is better understood as unseen. Sometimes the unseen part is dark matter, providing most of the gravitational framework inside and around galaxies and clusters. Sometimes it is dark energy, shaping the expansion of space on the largest scales. Sometimes it is ordinary matter that is simply too thin, cool, or faint to stand out in a dramatic image. Even NASA's description of dark energy says that space is never exactly empty, which means the instinctive picture of blank nothingness keeps shrinking as the evidence grows. Vera Rubin's line matters here because it captures the intellectual correction better than a technical slogan could. Observations forced astronomy to step away from the old confidence that visible matter was the whole story. The result was not embarrassment, it was expansion of understanding. The universe did not become less real when much of it turned out to be invisible. It became deeper, more demanding, and more honest. The visible part remained important, but it could no longer pretend to be the whole account. Rubin's work sits at the center of that change because galaxy motions were among the clearest places where preconception lost its grip. So the unsettling point in this chapter is also one of the most useful. Empty often means not shining, not there. A black sky region may still sit inside a dark matter structure. A widening universe may still be dominated by dark energy. The visible atoms that make up our world remain precious and decisive for chemistry, planets, and life, but they do not dominate the cosmic ledger. They live inside a universe whose larger architecture is set by things human eyes cannot simply look at and recognize. NASA's official numbers make that correction unavoidable. Ordinary matter is only a small fraction, while dark matter and dark energy dominate the total. If even the visible matter around us is only a small fraction of the cosmic whole, then the familiar solid objects of daily life may also be far less densely packed than they first appear. A table feels like the opposite of emptiness. You can rest your hands on it, knock on it, place a cup on it, lean your weight against it, and trust that it will answer with resistance every time. Nothing in ordinary experience suggests that such an object should be mostly open space. Yet when physics moved inward from the scale of furniture to the scale of atoms, that is exactly what it found. NASA defines an atom as a central nucleus surrounded by electrons, and NASA's current glossary states something even more striking. The nucleus holds more than 99.9% of an atom's mass, while occupying only about 0.01% of its volume. In other words, most of the atom is not a packed, solid interior. It is structure spread across a large region, whose mass is concentrated in an extraordinarily small center. That is one of the sharpest reversals in all of science. The objects that feel the most firm are not built the way human instinct first imagines them. They are not made like tiny stones cemented together with no room in between. They are made from atoms, and atoms are organized in a very different way. The tiny nucleus at the center contains protons and neutrons. Around that central region lies the much larger domain associated with electrons. NASA's glossary and Hubble's glossary both describe the same basic layout, a small dense nucleus at the center, surrounded by electrons. That simple picture is enough to overturn the everyday guess that matter must be densely filled all the way through in order to feel solid. The size contrast is so extreme that official science education sources often resort to scale comparisons just to make it imaginable. In a United States Department of Energy interview, nuclear physicist Kautar Hafidi described the nucleus as being like a small marble inside 5 football fields, while carrying 99.9% of the mass of the atom. In another Department of Energy educational guide, the comparison is slightly different but points in the same direction. If the nucleus were the size of a marble, the full atom would be about 100 yards across, roughly the length of a football field. These are not decorative metaphors. They are attempts to translate a real size ratio into something the body can picture. When that comparison lands, the table in front of you begins to look very different. This is also where the history matters. For a long time, atoms were imagined in much simpler ways, because no one had direct evidence for such extreme internal emptiness. The major turning point came in the early 20th century, when Ernest Rutherford and his collaborators studied how alpha particles scattered from thin metal foil. Most of the particles passed through with little disturbance, while a small fraction deflected strongly. Rutherford realized that this made sense only if most of the atom's volume was not filled with concentrated mass, and if the positive charge and most of the mass were packed into a tiny nucleus. The Nobel Prize record notes that Ernest Rutherford received the Nobel Prize in Chemistry in 1908 for his investigations into the disintegration of the elements and the chemistry of radioactive substances, and his later scattering work led to the nuclear model of the atom that changed how matter was understood. The table therefore feels solid, not because atoms are miniature billiard balls pressed flush together, but because the internal structure of atoms and the interactions between them produce strong resistance on human scales. At this stage, though, it is enough to stay with the size pattern itself. Once the nucleus is recognized as tiny and massive, a new image of matter appears. A table is made of atoms. Those atoms are mostly volume outside the nucleus. So, a table, when described in terms of atomic structure, contains a great deal of open region inside the boundaries we call solid wood, metal, or stone. NASA's recent glossary is unusually direct on this point, by stating the nucleus accounts for more than 99.9% of the mass, but only 0.01% of the atom's volume. The ratio is the heart of the surprise. That ratio also helps explain why the word space can be misleading here if heard too casually. It does not mean the atom is a hollow shell like an empty box. The electron part of the atom is not a few tiny pebbles orbiting through totally blank nothing. Modern atomic physics describes electrons in terms of quantum states and probability distributions rather than little planets circling in rigid tracks. NASA's glossary keeps the description simple by saying electrons orbit the nucleus, which is fine as a first picture, but the deeper point remains. The atom's size is set largely by the region associated with its electrons, while the nucleus remains dramatically smaller. So the atom is sparse in the sense of mass concentration, not built as a compact filled lump. This is one reason the transition from cosmic emptiness to atomic emptiness feels so strong. On the scale of galaxies, matter collects into islands and leaves huge regions between them. On the scale of atoms, mass again gathers into a concentrated center and leaves most of the atomic volume outside that center. The two cases are not governed by the same physics in every detail, but the emotional effect is similar. The world looks full from a distance because human senses respond to boundaries, surfaces, and resistance. The deeper structure often turns out to be much less crowded than surface appearance suggests. That is why a table can feel absolutely dependable and still be built from atoms whose mass is concentrated in tiny nuclei. Another useful detail comes from the way educational materials ask students to imagine atomic scale. In the Department of Energy Teacher Guide, one student can stand at the middle of a football field holding a marble to represent the nucleus, while other students stand far away to mark the region associated with electrons. The guide adds that the electrons themselves would be too small to see in that analogy. That teaching exercise works because the true ratio is so far from ordinary expectation. If you shrink the nucleus to something the hand can hold, the atom expands to the size of a stadium-scale space rather than to something just a little larger. Once that picture settles in, another common misunderstanding begins to loosen. People often hear that atoms are mostly empty space and jump to the idea that ordinary matter should therefore be fragile or ghost-like. But mass concentration and mechanical behavior are not the same thing. The table's solidity is not cancelled by the internal sparseness of atoms. The arrangement of electrons, the electrical interactions between atoms, and the quantum rules that govern how matter can be organized all matter enormously. The open region inside the atom does not make the table unreal. It simply means the internal architecture of matter is not what unaided intuition would predict. That fuller explanation belongs to the next step, but the groundwork is already here. A solid object can be built from atoms that are mostly volume outside the nucleus, without any contradiction at all. There is also something valuable here for the larger story of the universe. Empty often turns out to mean less concentrated than expected. Not absolutely nothing is present. In a cosmic void, there may still be gas, radiation, gravity, and dark matter. In an atom, there is still a real physical structure spread across the region we casually call empty space. The lesson is not that matter dissolves into unreality. The lesson is that human intuition usually overestimates how tightly packed reality must be in order to produce the world we feel around us. The table is one of the best examples because it seems so ordinary. Its familiarity hides how radical the underlying structure actually is. It is worth pausing on the phrase more than 99.9% of the mass. That means almost all the weight we associate with matter is concentrated in a tiny nucleus. If atomic volume were distributed in proportion to mass, the atom would look nothing like it does. Instead, nature gives us an arrangement in which the mass sits in an almost vanishingly small center compared with the total size of the atom. This is one of the reasons nuclear physics and atomic physics are distinct fields. The nucleus is tiny, dense, and governed strongly by nuclear forces, while the atom's larger-scale chemical behavior depends heavily on electrons and electromagnetic interactions. The everyday materials around us are shaped by both levels at once. Even though the nucleus occupies only a tiny fraction of the whole atomic volume, So the table is not a cheat, and the atom is not a paradox. The surprise comes only because the senses report one level of reality while science uncovers another. Touch reports firmness. Physics reports concentration of mass into tiny nuclei, with most atomic volume lying outside that dense core. Both statements are true. They are describing the same object from different depths. The Department of Energy's marble and football fields comparison and NASA's mass versus volume figures are powerful, because together they replace a vague slogan with a measurable structure. A table is not simply made of atoms. It is made of atoms whose internal geometry is radically more open than the surface suggests. If atoms are mostly open in this sense, why does a hand never pass through a wall, and why does a table answer every touch with such reliable resistance? This is where the idea of empty space inside atoms seems to collide head-on with ordinary life. A hand meets a wall and stops. A cup rests on a table and does not sink through it. Your feet press against the floor, and the floor presses back with such reliability that you almost never think about it. If atoms are mostly open in the sense we discussed before, then instinct expects some kind of failure in that contact. But the failure never comes. The reason is that solidity is not created by atoms behaving like tiny gravel packed without gaps. It comes from the way charged particles interact, and from the quantum rules that govern electrons when matter is pushed close together. Richard Feynman chose the atomic picture as the most information-dense sentence in science and wrote that all things are made of atoms. In the same opening passage, he added that these particles attract at some distances but repel when squeezed into one another. That short description already points toward the answer. The world resists compression because matter is structured, interactive, and constrained, not because it is internally featureless stone. The first layer of that resistance comes from electromagnetism. NASA's overview of the forces says, electromagnetism keeps electrons associated with atomic nuclei and allows chemical compounds to form. That matters because the outer parts of atoms, the parts that engage with neighboring atoms in ordinary matter, are governed strongly by electric charge. Electrons carry negative charge. Atomic nuclei carry positive charge because of their protons, while neighboring nuclei also repel one another because they are positively charged. In a solid object, what you call contact is mostly an interaction between electron clouds and electric fields, not a collision of tiny hard kernels. The wall does not need to be filled like cement with no internal openness. It only needs a stable atomic structure whose electrons strongly resist being forced into the same region as the electrons in your hand. That point becomes clearer if we avoid one misleading mental picture. Atoms are not miniature solar systems with little balls orbiting through emptiness in a way that leaves easy passageways between them. Even the simpler educational descriptions used by NASA, where electrons are said to orbit nuclei, are not invitations to imagine macroscopic holes that other atoms can casually slip through. The atomic scale is governed by quantum mechanics, and electrons are described by states and distributions rather than by neat little tracks. When two pieces of matter are brought together, those electronic structures begin to overlap in ways that are not freely allowed to continue without energetic cost. The result is that the closer the surfaces are pushed, the stronger the resistance becomes. Feynman made this point in another simple but very useful way. In his discussion of electromagnetism, he asked why protons and electrons do not simply collapse into a more intimate mixture if the electrical force is so strong. His answer was that the answer has to do with the quantum effects. That sentence matters because it prevents a common mistake. Electromagnetism by itself is not the full explanation for why matter occupies volume and resists unlimited compression. Electric attraction helps bind electrons to nuclei. Electric repulsion matters when like charges are pushed together. But the full stability of matter, especially bulk matter made of many atoms, also depends on a deeper quantum restriction. That deeper restriction is the Pauli exclusion principle. The Nobel Prize states that Wolfgang Pauli received the Physics Prize in 1945 for the discovery of the exclusion principle. In practical terms, for ordinary matter, this principle means identical fermions, such as electrons, cannot all pile into the same quantum state. This changes everything about how matter arranges itself. Electrons cannot all collapse into the lowest possible state in one tiny region and stay there. They must occupy different allowed states. That requirement builds up atomic structure, electron shells, chemical behavior, and, on larger scales, the fact that bulk matter occupies space instead of shrinking into a much denser, simpler lump. This is why a wall is not merely there in the everyday sense. It is defended by structure. When your hand approaches the wall, the electrons in the atoms of your skin and the electrons in the atoms of the wall are brought into increasing overlap. Electromagnetic interactions become stronger, and the exclusion principle sharply limits how those electrons can be arranged. The system responds by pushing back. You experience that response as solidity. There is no need for nuclei to touch. There is no need for atoms to be packed like beads in plaster. What stops your hand is the rising energy cost of forcing two organized quantum electromagnetic structures too far into the same region. Feynman's short phrase about atoms repelling when squeezed is a compact doorway into that much fuller picture. The importance of the Pauli principle becomes even more serious when physicists ask not just why atoms exist, but why ordinary matter remains stable in bulk. A major review in Reviews of Modern Physics by Elliot H. Lieb states that the Pauli principle, together with other facts from quantum theory, accounts for the stability of bulk matter. That statement is not about a minor correction. It means that without this quantum rule, the kind of extended matter familiar to daily life would not behave the way it does. Matter would not simply become a softer version of itself. It would fail to keep the same stable, space-filling character. The point is so strong that later mathematical work treated stability of matter as a deep theorem, level subject in physics, rather than a loose classroom slogan. This helps resolve a confusion that often appears when people first hear that atoms are mostly empty. They imagine the empty part as available room, as though another atom could simply choose a path through it. But the open region inside an atom is not empty in the practical sense of a hallway. It is part of an organized quantum object. The electrons associated with the atom are not optional decorations sitting far away from the nucleus. They are part of the atom's very existence as matter with size, chemical character, and response to forces. So when another atom approaches, it is not approaching a hollow shell that invites passage. It is approaching a structured region with charge distributions and quantum restrictions already in place. That is why the phrase, mostly empty space, is useful only if it is immediately followed by the reminder that the space is physically occupied by fields, states, and interactions. There is also a scale effect worth noticing. One atom by itself is already governed by these rules, but a wall is not one atom. It is an immense assembly of atoms, arranged through chemical bonding into a rigid lattice or network, depending on the material. When your hand meets that wall, you are not negotiating with a single electron cloud. You are pushing against an enormous collective structure whose atoms are already held in stable relation by electromagnetic interactions and whose electrons are already subject to Pauli restrictions throughout the material. That collective organization makes the response of solid matter strong, smooth, and dependable on human scales. The effect feels continuous because trillions upon trillions of atomic interactions are working together. A useful comparison comes from the way pressure behaves in extreme astrophysical objects. In white dwarfs and neutron stars, matter can be supported against further collapse by degeneracy pressure, a consequence of quantum rules related to the exclusion principle. That is not the same environment as a kitchen table, but it reveals the same basic lesson. The exclusion principle is not an abstract bookkeeping rule with no physical consequences. It has mechanical consequences. It changes how matter responds when compressed. In ordinary solids, those consequences operate at much lower densities alongside electromagnetic interactions. In compact stars, they appear in far more dramatic form. The same quantum logic that helps keep your hand from passing through a wall also appears, under very different conditions, in the physics of stellar remnants. This is also why touch is more subtle than it first appears. When you press your hand against a table, the atoms in your skin and the atoms in the table do not merge into one another. They approach until the energy cost of closer overlap becomes large enough that the table pushes back with a force balancing your hand. What you feel as contact is largely that balance of electromagnetic and quantum resistance. In that sense, the sensation of hardness is not evidence that matter is microscopically packed without openness. It is evidence that matter is extraordinarily effective at resisting certain kinds of overlap. Solidity is a behavior, not a simple visual description of internal packing. The same clarification helps with one more common misunderstanding. Sometimes people hear electromagnetic repulsion and assume that is the entire answer, while others hear Pauli exclusion and try to make that the only answer. The more careful view is that ordinary solidity involves both. Electromagnetic interactions govern much of atomic and molecular structure and become especially important as electron clouds and nuclei interact at short range. The exclusion principle determines how electrons are allowed to be arranged and prevents matter from collapsing into arrangements that would otherwise ignore fermionic identity. Feynman's wording is helpful because he mentioned both attraction and repulsion in the atomic picture, and then elsewhere pointed directly to quantum effects when asking why charges do not simply collapse together. So the answer to the original problem is less paradoxical than it first seems. We do not fall through walls because walls are not empty in the useful physical sense. Their atoms contain concentrated nuclei, extended electron structure, electric fields, quantum states, and rules that sharply constrain how matter can overlap. The open character of atomic size does not make matter ghost-like, it makes matter organized. The resistance you feel is the result of that organization doing exactly what physics says it should do. Feynman was right to treat the atomic fact as a kind of compressed map of nature. Once you unfold it, even the ordinary act of touching a table becomes a meeting between electromagnetism, quantum mechanics, and the large-scale stability of matter. And after that realization settles in, another deeper layer begins to stand out. If matter feels full because of fields and quantum structure, rather than because atoms are densely packed all the way through, then what we call empty space may itself be carrying more physical reality than sight alone ever suggests. The phrase empty space sounds simple until physics begins to lean on it. In ordinary speech, empty usually means nothing is there. No object, no furniture, no dust worth mentioning, no visible content at all. But when astronomy and physics use the word vacuum, they are not describing philosophical nothingness. They are describing a region where matter may be extremely sparse, while the underlying physical framework remains fully present. Even far from stars and galaxies, space still has structure, measurable properties, and effects that can be observed. NASA states that the cosmic microwave background is a faint glow that permeates the universe in all directions, and NASA also states that space is never exactly empty. That difference matters because it changes how the universe should be imagined. A cosmic void may contain few galaxies, but it is not outside the cosmos. Light still travels through it, gravity still acts across it. The geometry of space-time still defines distance, motion, and the path of radiation. The oldest light in the universe still passes through it as part of the cosmic microwave background, the remnant signal released when the universe became transparent about 380,000 years after the Big Bang. ESA's Planck materials describe the cosmic microwave background as the snapshot of that early era, and ESA's Cosmic Eras overview identifies recombination as the stage when the universe became transparent to light and left behind the diffuse microwave glow we still measure today. This is one of the first places where human instinct falls behind the evidence. The eye treats darkness as emptiness. A black region on the sky seems blank because there is no bright source announcing itself. But the absence of visible glow is not the same thing as the absence of physical content. The cosmic microwave background alone is enough to prove that. It does not come only from galaxies or nebulae. It fills the sky from every direction, which means even the darkest-looking reaches of space are crossed by ancient radiation that has been traveling toward us for most of cosmic history. NASA's explanation of the universe's baby picture says exactly that. The CMB is a faint glow that permeates the universe in all directions. The afterglow itself is already a strong clue that space is more than a passive stage. It carries information. The tiny temperature variations in the cosmic microwave background record the density pattern of the young universe, the one from which later structure grew. ESA's Planck summary explains that the tiny fluctuations seen in the CMB correspond to slightly different densities in the early universe and became the seeds of later stars and galaxies. So even where modern space looks empty, the radiation crossing it still carries a memory of the universe's earlier state. A region can be nearly devoid of stars and still be full of physical history. Gravity pushes the point further. In general relativity, gravity is not a mysterious pull acting through a featureless void. It is tied to space-time itself. Stanford's Gravity Probe B educational material explains that one of the direct predictions tested by the mission was the geodetic effect, meaning the amount by which Earth's mass warps the local space-time around it. Another Stanford relativity explanation states that in general relativity, the gravitational field is identified with the metric structure of space-time. That means space is not just an empty container where gravity happens to operate. Its geometry is part of what gravity is. Once that idea settles in, empty space begins to look less like absence and more like a medium with rules. Not a medium in the old 19th century sense of ether, but a physical arena with geometry, measurable behavior, and field content. Light does not simply move through nothing, as though nothing had to be specified. The speed of light in vacuum is a defined physical constant, and space-time curvature affects how clocks run and how light propagates in gravitational fields. Stanford's relativity material states that in any local reference frame, the speed of light in a vacuum is fixed, and the same educational archive repeatedly treats local space-time geometry as physically meaningful rather than as a mere backdrop. Then modern quantum theory makes the picture even less bare. NASA's current dark energy overview says that space is never exactly empty and notes that, according to quantum field theory, transient particle-antiparticle activity is associated with vacuum energy. That does not mean every popular simplification about virtual particles should be accepted uncritically, and it does not mean dark energy has been fully explained. NASA is clear that the nature of dark energy remains unknown. But the important point for this discussion is narrower and firmer. Present-day physics does not treat vacuum as simple nothing. It treats it as a state with physical meaning, one that can still be associated with fields and energy. That is why the word vacuum is safer than the word nothing. A vacuum means no substantial amount of ordinary matter in the region being described, or at least much less than in denser environments. It does not mean reality has been removed. Radiation can still pass through. Gravitational influence can still cross the region. Quantum fields are still part of the description. Even the average expansion of the universe is a property of space-time itself, not of luminous matter alone. NASA's dark energy page frames accelerated expansion in terms of the behavior of space, and NASA's universe materials tie the cosmic microwave background, expansion of space, and early universe physics into a single physical story, rather than a collection of disconnected objects floating in emptiness. There is a useful contrast here with the older philosophical habit of asking whether nothing exists. Physics usually steps away from that wording because it is too absolute to be measured. Science does better with quantities that can be observed, modeled, or tested. A region of intergalactic vacuum can be characterized by temperature, radiation passing through it, curvature effects, particle fields, density contrasts, and expansion behavior. Those are not decorative ideas. They are measurable parts of the theory and observation framework. ESA's Planck work turned the faint microwave glow of the sky into precision cosmology, and Gravity Probe B measured relativistic spacetime effects near Earth with gyroscopes in orbit. Neither achievement would make sense if space were treated as mere philosophical absence. This also helps explain why the universe can feel visually sparse and physically rich at the same time. If you remove bright stars, glowing gas clouds, and obvious galaxies from a region, the eye reports little to see. But physics still sees spacetime, background radiation, gravitational structure, and vacuum described by field theory. The region has become harder to photograph in a dramatic way, not meaningless. NASA's explanation of the CMB and its dark energy overview are especially useful together here. One tells us that ancient radiation fills all directions, and the other tells us that space is not exactly empty, even where visible matter is absent. Put together, they make the idea of pure nothingness much harder to defend as a description of real cosmic vacuum. James Webb and earlier missions add another layer to this picture by showing how far back the universe can be studied with light. NASA's Webb Early Universe page explains that the cosmic microwave background marks the earliest point in cosmic history that we can observe with any form of light before the later era when stars switched on. That means the background itself is not a side detail. It is part of the basic physical content of the universe, long before galaxies crowded any image. Empty-looking space still carries the remnant signal of that young era, stretched by expansion into the microwave range we measure today. Once this is understood, the phrase empty space becomes a kind of shorthand rather than a literal verdict. It usually means no nearby stars, no dense gas cloud, no ordinary matter concentration large enough to shine brightly or gather into a visible object. It does not mean no physics is present. It does not mean no radiation crosses the region. It does not mean no geometry is there to be curved, no vacuum state to be described, and no gravitational field to matter. In modern cosmology, a vacuum can still participate in the story of expansion, and in modern relativity, space-time itself is part of the story of gravity. That is why the older intuition has to be revised with some care. The universe is not mostly full in the way everyday objects are full, but neither is its emptiness a literal null state. Between galaxies, and even inside the great sparse reaches of cosmic voids, space remains physically active in the sense that it carries radiation, supports fields, obeys geometric laws, and takes part in cosmic expansion. The darkness between bright objects is real, but darkness is not the same thing as absence. NASA's and ESA's descriptions of the CMB, together with NASA's statement that space is never exactly empty, push that correction firmly into place. If vacuum is physically real, and if even the darkest parts of the universe are crossed by ancient light and shaped by fields and geometry, then the future of the universe may not simply be a story of objects moving apart. It may also be a story of space itself taking a larger and larger role in what the universe becomes. Why is the universe becoming even emptier as it ages? The universe is not only sparse, it is becoming more sparse with time. That shift is one of the hardest parts of the story to hold in the mind, because it asks you to stop thinking of emptiness as a fixed background and start seeing it as a growing condition of cosmic history. For a long stretch after the Big Bang, gravity worked against expansion, slowing it down. Then, the pattern changed. NASA states that 9 billion years after the universe began, its expansion started to speed up, driven by what scientists now call dark energy. The Department of Energy describes this as the second major period of cosmic acceleration, beginning about 9 billion years after the Big Bang and continuing today. That one change alters the long future of the universe. If expansion were only continuing at a steady pace, the cosmos would already be wide and thin. But acceleration means that, on the largest scales, distant galaxies are being carried away from one another ever more effectively. NASA's Dark Energy Overview explains that the expansion is speeding up rather than slowing down, and ESA says cosmological observations showed that the universe does not expand at a constant rate. Its expansion is accelerating. This does not mean that every structure everywhere is flying apart internally. Galaxies held together by their own gravity do not simply dissolve because cosmic expansion exists. Galaxy clusters that are already gravitationally bound can remain bound as well. The change is most important on the largest scales, where space between distant structures keeps increasing. So the future emptiness of the universe is not mainly the story of stars inside a galaxy scattering away from one another. It is the story of the great separations between major structures becoming larger, while the already empty reaches between them take up even more of the cosmic volume. NASA's Roman dark energy page explains that observations of distant supernovae showed the universe expanded more slowly in the past than it does today, which means the large-scale gaps are not static background features, they are widening. That is why the phrase "becoming emptier" is not just emotional language. It has a physical meaning. Average matter density falls as the universe expands. If the volume available to matter keeps growing, while the amount of ordinary matter on the largest scales is not increasing to match it, then the average density drops. The universe becomes more dilute. At the same time, the acceleration makes it easier for already distant regions to lose contact with one another in any practical sense. The visible structures remain where gravity has already gathered them, but the great reaches between those structures continue to stretch. NASA's dark energy page ties this directly to the expansion history of the cosmos, and ESA's Euclid mission states that one of its central goals is to investigate the origin of the accelerating expansion itself. The discovery of this accelerating future was one of the great reversals in modern cosmology. For a long time, the natural expectation was that gravity should steadily slow the expansion down. Matter attracts matter. A universe filled with matter ought, at first glance, to behave like a thrown object losing speed under a persistent pull. ESA says this was the older expectation. Matter and energy in the universe were thought to cause expansion to slow over time. Then observations in the 1990s showed the opposite trend. The universe was not merely continuing to expand, it was accelerating. NASA's Hubble materials and dark energy pages both frame this as one of the major surprises of late 20th century astronomy. That surprise matters here because it changes what empty will mean in the future. Right now, when telescopes look outward, they still see a universe rich with galaxies over enormous distances. Surveys trace filaments, clusters, walls, and voids. But if accelerated expansion continues, then over enough time the large-scale universe becomes less connected in observation as well as in geometry. Distant galaxies recede farther. Light from very remote regions becomes harder to detect. The cosmic landscape, viewed from any one bound region like our local group, would appear increasingly isolated. NASA's dark energy material and ESA's Euclid mission framing both treat accelerated expansion as a dominant, late-time feature of cosmic history. There is a useful distinction to keep clear here. The universe becoming emptier does not mean it is running out of physics. Space still carries geometry, radiation, fields, and the effects of dark energy. What changes is the large-scale distribution of matter and the distance between major concentrations of it. In other words, the future universe may be physically rich in law and structure while becoming visually poorer in nearby cosmic company. A galaxy like the Milky Way may still contain stars, planets, gas, dust, magnetic fields, and stellar remnants. But beyond its gravitationally bound neighborhood, more and more of the cosmos would lie at tremendous remove. That is a very different kind of emptiness from the emptiness inside an atom or the low density inside a cosmic void. It is historical emptiness, growing with cosmic time. NASA's wording about the timing of acceleration gives this history a particularly sharp shape. The universe is about 13.8 billion years old, and the expansion began speeding up about 9 billion years after the beginning. That means acceleration is a relatively late chapter, not a property that dominated from the first moments onward. Early on, the universe was hot, dense, and expanding rapidly. Later, gravity slowed that expansion. Later still, the balance shifted and acceleration took over. So the cosmos has not been marching under one simple rule from start to finish. Its large-scale behavior has unfolded in stages. NASA's Cosmic History Overview describes the age of the universe as about 13.8 billion years, and NASA's Dark Energy page gives the transition to speeding up expansion at roughly the 9 billion year mark. This is one reason dark energy remains such a central problem. We can describe what it appears to do more easily than we can explain what it is. NASA repeatedly describes dark energy as an unknown force or unknown cause associated with accelerated expansion. ESA likewise presents Euclid as a mission meant to investigate the nature of dark energy because the underlying cause is still unresolved. So when we say the universe is becoming emptier as it ages, we are describing an observed large-scale trend whose driver is still one of the major open subjects in physics. That uncertainty does not weaken the main picture. The observational result is strong. Supernova data in the 1990s first revealed the acceleration, and later missions have kept refining the cosmic expansion story. NASA notes that Hubble observations of distant exploding stars helped show that the universe expanded more slowly in the past than it does today. ESA describes Euclid as a mission dedicated to investigating the origin of that accelerating expansion. The cause is still debated in detail, but the broad trend is not a guess. This growing emptiness also changes the emotional scale of cosmic time. In the earlier universe, galaxies were on average closer together. Interactions and mergers were more common. The visible cosmos was denser in that historical sense. As time goes on, the opposite trend dominates large scales. Separation grows. Isolation increases. The future universe is not merely old, it is stretched, and that makes the present era unusual. We live at a time when the universe is old enough for heavy elements, planets, chemistry, and life, but not yet so expanded that the larger cosmic environment has faded entirely from view. That is one reason Carl Sagan's line still carries weight here. We are a way for the cosmos to know itself. The Carl Sagan portal attributes that line to Carl Sagan, Anne Druyan, and Stephen Soter. In the context of cosmic expansion, it lands with special force because the knowing happens from inside a temporary window when much of the universe is still observable. That line does not change the physics, but it does sharpen the scale of what the physics means. Matter organized itself into stars and galaxies. Chemistry arose in a small portion of that matter. On at least one world, that chemistry became capable of asking what the universe is doing. And one answer now seems unavoidable. On the largest scales, the cosmos is moving toward greater separation. The universe is not only old, it is opening up. It is becoming thinner in its matter distribution and more distant in its large-scale relationships. There is no need to force this into catastrophe. The galaxies around us do not vanish overnight. Bound systems remain bound. Stars continue their own lifetimes. Planets continue their orbits. But the larger setting changes steadily, and in that setting the average condition becomes more sparse. The same cosmos that once grew structure from tiny density differences now continues into an era where dark energy shapes the largest distances more and more strongly. NASA and the Department of Energy both describe this late-time acceleration as an ongoing feature of the universe we inhabit. So the title of this part has a clean scientific answer. The universe is becoming even emptier as it ages because the expansion of space is accelerating, increasing the great separations between distant structures and lowering average matter density on the largest scales. That does not erase local structure, but it does change the long arc of cosmic history. The future is not simply more of the same. It is a universe in which space itself takes on an even larger share of the story. From this perspective, a different interpretation begins to emerge. The universe grows emptier over time, yet structure depends on that very emptiness. Stars, planets, chemistry, and observers appear within a cosmos where space is mostly unfilled. And that brings us to, could the universe be mostly empty? Because emptiness is what allows structure to exist at all. By the time we reach the end of this subject, emptiness no longer looks like a defect in the universe. It begins to look like one of the conditions that made structure possible in the first place. The universe is not arranged like a block of matter packed without relief from one edge to the other. On the largest scales, galaxies, galaxy groups, clusters, superclusters, and walls sit inside a cosmic web with large voids between them. NASA describes that arrangement as twisting, thread-like large-scale structure with concentrations of galaxies and voids of space in between. That pattern matters because it means the universe did not build everything everywhere at once. It built structure by allowing matter to gather here, remain separate there, and evolve over long spans without being crushed into one uniform state. That separation is not decorative. It changes what can happen. A stable planetary orbit requires room. Earth can remain at roughly 1 astronomical unit from the Sun because the solar system is not a crowded swarm of stars pressing in from all directions. NASA notes that the Sun is about 93 million miles, or 150 million kilometers, from Earth, and that life as we know it depends on the Sun's energy. NASA's habitable zone explanation adds that there is a specific range of distances from a star where liquid water can exist on a planet's surface. That only makes sense in a universe where matter is sufficiently spread out for long-lived orbital systems to remain organized. If stars were packed far more tightly on average, gravitational disturbances would be more common. Stable planetary climates would be harder to maintain, and the long patience required for chemistry and biology would be much harder to sustain. The same logic applies to stars themselves. A star is not a random flame suspended in a crowded medium. It is a self-gravitating object whose lifetime depends on balance. NASA explains that once fusion begins, a star enters the main sequence, the longest stage of its life, in which hydrogen fusion is stable. NASA also notes that the Sun is a 4.5 billion-year-old yellow dwarf star, still in that stable stage. This matters because heavy structure in the universe depends not only on matter existing, but on some of that matter remaining in stable stars long enough to build elements, warm planets, and maintain conditions over immense timescales. A universe with no room for long-lived, stable stars would be a very different universe from the one that produced chemistry, planets, and observers. Emptiness also matters at the scale of galaxies. NASA's large-scale structure page says the web forms as gravitational attraction draws matter together, producing concentrations of galaxies with voids of space in between. The Roman Wide Area Survey description adds that galaxies assembled along vast strands of gas, separated by large voids, and that as the universe expands, the density of galaxies within a fixed, large volume decreases with cosmic time. That means structure is not merely a matter of piling objects together. It is a matter of arranging them with enough separation for the web itself to exist. filaments become meaningful because voids define them. Clusters stand out because surrounding regions are less dense. On large scales, order is not the opposite of emptiness. Order partly depends on emptiness. The chemical side of the story points the same way. The Big Bang did not begin with the full chemical richness we know today. NASA's Hubble material on an ancient star explains that the early universe produced mostly hydrogen, helium, and traces of lithium, while heavier elements such as carbon, nitrogen, and oxygen were built up later through nuclear reactions in successive generations of stars. NASA's star overview explains that high-mass stars continue fusing heavier and heavier elements until iron appears in the core, and Webb observations in 2023 identified heavy element production from a neutron star merger. Chemistry therefore required time, stellar processing, explosive events, and dispersal through space. That sequence depends on matter not being crushed into one static state everywhere. It depends on stars being separate objects with their own lifetimes, deaths, and contributions to the wider medium. Once those facts are placed side by side, the older instinct begins to weaken. It is tempting to imagine that a more matter-filled universe would somehow be a more productive universe. But much of what we value in cosmic structure comes from gradients, spacing, and persistence over time. Planets need room to orbit. Stars need long, stable phases. Galaxies need enough separation to remain distinct systems rather than one uniform mass. Chemistry needs repeated generations of stellar birth and death. The universe did not become productive by filling every location equally. It became productive by letting matter collect into islands of structure inside a much larger sea of lower density space. That inference is consistent with the observed cosmic web and with the known history of element formation in stars. Even on the scale of a single planetary system, spacing is doing quiet but essential work. NASA's habitable zone description is simple and severe at the same time. A planet must lie at the right distance from its star for liquid water to remain possible at the surface. Too close and water is lost to heat. Too far and it freezes. The important point here is not only that there is a favorable zone, it is that orbital structure must remain stable enough for a planet to stay in it over long periods. That requirement is easy to miss because human attention is drawn to dramatic events like impacts, stellar explosions, or galactic collisions. But the existence of long, uninterrupted orbital stability may be one of the quietest and most important products of a universe that is not overpacked. The same principle appears again inside stars. Stable main-sequence fusion is possible because gravity compresses the star strongly enough to heat the core, while pressure from fusion pushes back. NASA describes the main sequence as the long, stable stage of stellar life. That word stable matters more than it first appears. If the universe only favored violent compression without these long, balanced phases, then stars would not serve as long-duration engines for chemistry and planetary environments. The fact that most stars spend the longest part of their existence in a stable state is one of the reasons cosmic evolution has time to do more than simply burn bright and collapse. There is also a broader geometric point. NASA's large-scale structure page and Roman survey materials show a universe where matter is organized into filaments, clusters, and voids, not into one continuous slab. That geometry allows different scales of structure to coexist. A star system can live inside a galaxy. A galaxy can belong to a group or cluster. A cluster can sit at the intersection of filaments. Between these structures lie large, underdense regions. If the cosmos were not arranged with that hierarchy of concentrations and separations, many of the stable environments we now take for granted would either never form or would be disrupted more often. The web is not just a pretty map. It is the large-scale expression of a universe that makes room for layered structure. By this stage, emptiness begins to look less like a subtraction and more like a framework. It is the reason stars are not jammed together everywhere. It is one reason galaxies remain distinguishable systems. It helps create the low interference conditions under which orbits can persist and chemical history can unfold step by step. Even the present universe, where average matter density keeps falling as expansion continues, still carries the older lesson written into its structure. Not everything valuable comes from packing more matter into less room. Sometimes the ability of matter to stay apart is what gives complex order a chance to exist at all. That conclusion fits the observed history in which the density of galaxies within large cosmic volumes decreases as the universe expands, while structure still remains visible along filaments and in bound systems. This does not mean emptiness alone creates structure. Gravity, nuclear fusion, electromagnetism, quantum rules, and cosmic expansion all take part. But emptiness is part of the working arrangement, not its enemy. A solar system needs room around a star. A galaxy needs room around neighboring galaxies. Chemical enrichment needs space for stellar debris to mix, cool, and later enter new stars and planets. A habitable world needs distance to be neither too hot nor too cold. When these facts are placed together, the final picture becomes harder to resist. The universe is not mostly empty because it failed to build. It may be mostly empty because building on many scales requires separation as much as concentration. That is why the closing thought of this series does not need a dramatic reversal. The reversal has already happened. The thing that first seemed like absence has turned out to be part of the design by which stars, planets, galaxies, and chemistry remain possible. The voids between filaments, the distances between stars, the spaces inside atoms, the low density reaches between galaxies, and the long intervals of stable stellar burning all point toward the same correction. The universe did not become rich by filling every available place. It became rich by allowing structure to emerge inside a much larger setting where space itself had room to matter. If you stayed with me all the way to the end of this long journey, thank you. I truly appreciate your time, your attention, and the trust it takes to spend part of your day or night here with me. If this video gave you something worth carrying with you, a like or a soft tap on subscribe would be a real source of encouragement for me to keep making these science stories. And if you feel like sharing, I would love to know where you are listening from, what time it is where you are, and what you would like me to explore next. I hope the rest of your evening feels easy. I hope your mind gets the rest it needs. And I hope you wake into a new day with a little M.